ये अपने जो क्विजेस है लास्ट टाइम वो करेक्ट कर लीजिएगा बाद में. So let's begin. Last time we were studying electromagnetic plane waves. And we saw that if, say, we have a wave propagating along, suppose, z-axis, the electric and magnetic field can be written as, so this is x-axis, this is y-axis. So in vacuum, almost forget the spelling of vacuum. In vacuum, if the electric field is, let's say, along x-axis and have some magnitude E naught, can be written as this. And if the electric field is like this, the magnetic field is along a direction which is perpendicular to this and this. And its magnitude is given by this, where c is speed of light in vacuum. So the electric field is perpendicular to magnetic field and is perpendicular to the direction of propagation z. Similarly, magnetic field is perpendicular to electric field and direction of propagation. And the arrangement is such that E, H and K, they form a right-hand system. The direction of E, direction of H and direction of K is a right-handed triad. That if this is, let's say, x-axis, this is y and then this is z. If this is x-axis, this is y, this is z, and so on. So you curl your fingers from E to H, your thumb should point in the direction of K. We had a quick quiz last time, which was that suppose the plane wave is propagating in the xy plane, making an angle theta with the x-axis. So the direction of propagation, let's call it k hat, is x cosine theta plus y sine theta. So we have to choose electric field and magnetic field such that they fulfill this criteria. So we wrote electric field by arbitrarily choosing it to be along z-axis with some magnitude E naught. So this K vector can be written as K dot R, where R is x hat, y hat, z hat, etc. So this K dot R will become x cosine theta minus y sine theta. So this was electric field, and the question was, what is the magnetic field? Surprisingly, about half of you didn't answer correctly. So B has to be perpendicular to both Z and to this direction of propagation. Okay? It doesn't have to be perpendicular to only one thing. So some of you wrote just that B is along y-axis, okay, which is perpendicular to Z, but it's not perpendicular to the direction of propagation. So that's not valid. So let's first find the direction of B. Some of you tried using Maxwell equation, which is fine. So B is perpendicular to E and K. So it means it should be like this. Let's say this is unit vector. So K is this is Z. So X cross Z is minus Y cosine theta, and Y cross Z is X. So this is the direction of magnetic field. And its magnitude is this. So this is B. So let's check that if this is perpendicular to this, but does this make a right-hand system? That also has to be checked. So the direction of this vector is, so this has a negative y component and a positive x component. So this vector should be a negative y component and a positive x component. So this vector would be directed in this direction. So the electric field has been taken along z-axis out of the board. So let's see, if I curl my fingers from electric to magnetic field, yes, the thumb does point in the y direction. So you have to make this check, because when it was computing this direction of B field, you could have taken it like E cross K. So then there would have been a negative sign. So just this rule that we derived from our field expression for electromagnetic plane waves that we worked out for a uniform current sheet. So you can use this thing here. We can actually make it more systematic, as we are going to do today, so that you don't have to remember anything. So there are a certain set of laws. And you can always use Maxwell equation. If you have an electric field, you want to find magnetic field, substitute this electric field in Maxwell equation and find the magnetic field. You can do that as well. But before we go on to further discussion of plane waves, let's introduce a notation which is very useful for plane waves. This is called phasor notation. Because in plane waves we are dealing with sinusoidal functions, and when we take the, let's say, derivative, cosine goes into sine, sine goes into cosine, but the argument remains the same, and then there's a factor multiplying there. And we can do that thing easily if instead of using cosine and sine, we use exponential function. And we develop a notation like this. If, let's say, we have an electric field like this, we can equivalently express it like this, that this is real part of this function, where this thing is E naught potential minus iota E naught. And this thing is called the phasor. So instead of writing this field, we only write this field. In some books, you see exponential iota omega t written as well, but you don't have to write that as well because that just keeps going along with all the equations. So it's redundant. So this is the notation that we have introduced to work with. So whenever we are going to do the computations, we are going to use this expression instead of this, but we have to remember that this is not the electric field. Whenever you want to get the actual electric field, you multiply it with exponential iota omega t factor, take its real part, and that will give you the electric field, because electric field is a real quantity. Similarly, magnetic field and so on. And this is the complex quantity. So to get the real quantity, you multiply it with this factor, take real part, you get this. Similarly, for magnetic field, we can write it like this. The phasor and the time part. Essentially, we are separating the spatial and temporal part, where this phasor is given by this. So this is our plane wave notation. So whenever you see this part, you should always think of a plane wave, that this represents a plane wave. This represents a plane wave. Now so far we have dealt only with electromagnetics in vacuum. And let's now introduce materials, and then we will see how we can work with plane waves and what properties of plane waves are in materials. So let's discuss the basic types of materials. We can think of materials as of two types, the simple materials. We are not going into anisotropic materials. So isotropic materials can be categorized into, let's say, dielectric materials, magnetic material, dielectric magnetic material. So in dielectric material, we introduced a parameter called permittivity, which is equal to a scalar multiple of the permittivity of free space. This epsilon naught is the permittivity of vacuum. And the permeability is still mu naught. So dielectric materials are materials whose permittivities are different than vacuum, but their permeability is the same as that of vacuum. And that's actually what most materials are, like air, water, wood, even V. So everything is almost dielectric material. The permeability doesn't go away much from mu naught. So let's say for most dielectric materials, mu is equal to 0.99999 term mu naught. So it's almost mu naught. Then we have a small class of materials which is called magnetic material. In these materials, the, let's say, permittivity is that of vacuum, and permeability is a scalar multiple of permeability of free space. These are scalar number, These are called relative permittivity. This is called relative permeability. And these are very rare material. Most magnetic materials are actually dielectric magnetic material in which the permittivity is also different and permeability is also different from the permeability of free space. There are certain materials which have their permeability different from that of the free space permeability, and since they are material, so usually their permittivity is also different from the permittivity of vacuum. So these materials technically are called dielectric magnetic material, which in common language are only called magnetic materials. But they are also dielectric as well because the permittivity is different from vacuum. These magnetic materials in true sense do not exist, because if you want to have permittivity to be equal to permittivity of vacuum, essentially you don't have to have any material. And if you don't have a material, then there's no permeability response. So these are the rough categories of materials that we can categorize dynamically. जिनको नॉर्मली हम मैग्नेटिक कहते हैं, they are actually both. They are dielectric as well as magnetic. हम उनकी word magnetic ही use करते हैं to differentiate them from dielectric material. But in true sense, they are dielectric as well as magnetic material. क्योंकि just magnetic हम उनको कहेंगे जिनकी जो permittivity है वो free space permittivity हो और सिर्फ permeability different हो. जिस तरह डायलैक्ट्रिक हम उनको कहते हैं जिनकी परमिएबिलिटी वैक्यूम की परमिएबिलिटी है और परमिटिविटी डिफरेंट है, ठीक है? तो जिनकी दोनों डिफरेंट है, दे आर टेक्निकली डायलैक्ट्रिक मैग्नेटिक आइसोटोपिक. Okay. The formalism that we have developed so far remains almost the same. All we have to do is change the permittivities with the permittivity of free space with these permittivities. So we get del dot E rho over epsilon, del dot B is still 0, del cross E is still this, and del cross this becomes now this. For both dielectric, magnetic, dielectric, for all of these. Because I'm using a different mu and a different epsilon. So now let's get back to our plane wave, but in material. So these are our Maxwell equations. Let's be concerned only with the characteristics of plane waves, not their generation, which we saw in the last lecture in vacuum. So let's take this J and rho to be 0. So in source free regions, the equation becomes this. Let's now introduce the phasor form. The fields here are R and T dependent in all the cases. So let's introduce the phasor notation. For phasors, this B and E, they are represented in this and in this fashion. So we have this phasor into this thing, this phasor into this thing. So if I substitute E of RT with this thing, we get this equation still the same. This equation is still the same. This equation will be, so let me just work it out this one so that we know how it is converted. So we have the time dependent Maxwell equation like this. So let's substitute the phasor notation. This is the phasor. So since this is all real, the real part of this thing into this is the same as the real part of since this is the time dependent part and this is only a special operator, we can take this thing out of this here. Similarly, this is so this becomes, this is constant with respect to time, so we have iota omega B of R so we get this. Now for computational purposes, not, we can think of it in both ways. Okay, क्योंकि ये जो K है, this can be complex and real. If it is complex, it has a real and imaginary part. तो जो imaginary part है वो iota के साथ multiply होके वो iota खत्म हो जाएगा. फिर जो imaginary part वाला K है, you can take it outside and you can pair it with this thing. Or you can, if you think of this as complex number, you can an R dependent part. So this part is usually devoid of any phase. So if this K is real and we think of this to be lossless plane wave, then this is independent of R. But if it is going on in lossy medium, we can either think of B to be R dependent, or we can think of B to be constant and K to be complex. So
in general, if you want program not sure, so उसकी only dependence is e to the minus r.
जी जी.
तो ये कोई और dependence नहीं हम डाल सकते.
For plane waves,
it's plane waves. हाँ. In a sense, we already solved this one.
जी. So for plane waves, this B can only have a dependence of exponential minus R something, and no other R dependence. Okay. So this thing, for calculational purposes, instead of going on solving this equation, we can solve this equation. And find the phasors. So when we have the phasors, we can either put them in this equation and take the real part and get the corresponding equation, But instead of doing that, we can also put this EB into the definitions of the phasors and compute the real field. So instead of working with this equation, we can work with this thing. Minus iota omega b. So essentially the time derivative is replaced with iota omega. Similarly, this equation for phasors is E, so there's iota omega E of R. So these are Maxwell equations for plane waves. Actually, not for exactly for plane wave, but for, you can say it in phasor form. Or there is a better term, it's called the equations for time harmonic fields. So whenever we have fields that are harmonic in time, that their time dependence is sinusoidal, then we can use these equations instead of those. So let's use these phasor equations to find the properties of plane waves. So the plane wave can be represented as in phasor form like this, and the magnetic field like this. So let's try to find out E naught, B naught, and K in a medium. So to do that, we have to substitute these equations into Maxwell equations. So in the first equation, this becomes this. So this is now the divergence of a vector into scalar. Did we have identity of this type in homework 1? What's the divergence of a vector into scalar? It's the divergence of the vector and the scalar as it is. This is out of the differentiation plus the vector dot gradient of the scalar. So this is the chain rule for del dot, just as we have the product rule for derivatives. So it's almost like that. Now this is 0 because we are assuming E naught and B naught to be independent of R, which they are for plane waves, and that exponential dependence we have kept in this K. So this is 0, and we have to evaluate this derivative. So if you evaluate this derivative, this comes out to be minus iota K function minus iota B. It's very easy. Assume K to be like K1x, K2x, K3x, and R, X, Y, and Z, and take dot product and then operate this del. This simply comes out to be like this. Now, if we put this thing here, we have minus iota K dot E naught equals 0. So this minus iota we can, since there's a 0 on the other side, neglect it. Now here, this is a function of R. And this can be 0 at all R. Otherwise, the field is 0. So it means this coefficient has to be 0 to satisfy the first Maxwell equation. So this is the first condition on plane waves in dielectric magnetic medium which are isotropic. mediums. That the k vector and E naught has to be perpendicular. Similarly, if you put this thing in the second Maxwell equation, you will get k dot B naught equals 0. So this B naught also has to be perpendicular to k. And if we put this E and B in the third equation, we get del cross E naught k dot R minus iota omega V naught k dot R. Now, similarly, we have a product rule for the curl of a vector into scalar, which is that let's say we keep first the scalar as it is and then take the curl of the vector plus the gradient of the scalar crossed with the vector. So this becomes this. Now this is 0 again because E naught is a constant, so its derivatives will be 0. So this factor goes away, and the del of this is minus iota k into exponential minus iota k dot R. Oh, there's a B naught here. This minus iota goes away, we can write it as k cross E naught minus omega V naught. Again, since this can't be 0 for all R, this must be 0, which means that k cross E naught equals omega B naught, or B naught is so I wrote k as k hat into k magnitude and took omega here. So it means if you have the electric fields vector, you can find the magnetic field by taking its curl with the unit vector along k and multiplying with this factor k over omega. Because E naught and B naught are constants. Yeah. Okay, so if we put this E and B in the last equation, we get, try to write it directly, we will get E naught as minus k over omega mu epsilon k hat cross. So this is the equation. If you have V naught, you can find E naught simply by taking the cross product, but no, you have to use minus sign here. Okay. So you see one thing. We haven't been able to find the value of E naught or B naught, but what we have been able to find is the relationship between them. So we still have a choice. For example, I can choose the magnitude of B naught to be whatever I like. But once I have chosen the magnitude of B naught, its direction should satisfy this thing. And once its direction is given and magnitude I have already chosen, I can put the magnitude and direction in this B naught vector here K here and find E naught. So one thing we can fix. The other things will follow from here. And about K, we haven't been able to say anything about K. So let's try to find any condition for K. To do that, let's say we take the K hat cross for this equation. So on this equation, on both sides, let's take K hat cross. So we get K omega K hat cross K hat cross E naught. The value of this K hat cross B naught we can write from here, which is minus omega mu epsilon over K into E naught, and on this side we can open this triple cross product as K hat dot E naught minus K hat into E naught. This is 0, right? Because we know K dot E naught has to be 0. So we get, let's take this K there and this omega here, get omega square mu epsilon dot, this is K square. K hat dot K hat is 1, so we get this. Which means that K square must be omega square mu epsilon. So this is the only restriction that we have about K. That its magnitude square must be equal to this thing. For plane waves, they are in phase. In isotropic homogeneous field. And actually we computed the electromagnetic field from a fictitious infinite Planck sheet just last lecture. We found that they are both in phase. For plane waves, there are situations where we can create phase difference and we can get other things, but they're not plane waves. Okay, so if you have a medium specified by epsilon and mu, and you want to write the plane wave solution in them, you can choose a frequency, so you know omega. So then you can find the magnitude of K from here. You are free to choose the direction of propagation. So you can, let's say, choose a direction of propagation. So K hat is arbitrary. There is no restriction from Maxwell equations that what it has to be. So you can choose it, but the magnitude has always to equal to be this. So K hat, once you choose K hat, the direction of E naught and B naught are also fixed because they have to be perpendicular to that. So there are actually only two choices that we can make. The one is that K hat is arbitrary, we can choose it to be whatever we like. And the second is the magnitude of one of the fields, of either E naught or B naught. Once this and one of these is chosen, everything else is fixed. Omega we have to choose. So, because equations are valid at any frequency. And why do we have this freedom in this solution that we did? Because we didn't consider the sources. We are working in source-free region. So if you consider sources, then everything is fixed. as we found in the last lecture, that once we imagine that there is an infinite sheet in xy plane with the current going in this direction, then the plane wave can only go in this direction and this direction as it happened in that one. And then the direction of electric field and the direction of magnetic field was also fixed. Their magnitude was also fixed. So everything was fixed by source. So here, since we haven't considered sources, we can take any direction of propagation, because then corresponding to that direction, there is, let's say, a fictitious current sheet perpendicular to that which is radiating there, and we can arbitrarily choose the magnitude of the current, so we can choose the magnitude of the field at will as well, and we can choose the magnitude of frequency for the current, so omega is also arbitrary. So that's why we have these choices, because we have not considered any sources to fix these things. Okay, so let's take a couple of examples of some materials and see what do they represent. And before we do that, let's just do one quick thing. Let's say I have the electric field like this. If K is real, and let's take, so R is always this. We don't take R to be like this, R is always this. But let's take the direction of propagation to be z-axis, and the magnitude of K, let's take it to be complex. So if it is complex, then the electric field becomes into Z equal, so this is exponential minus iota K prime Z, and minus iota into iota is iota square minus minus plus, so this is K prime Z D minus iota K prime Z. क्या कह रहे हैं? इस नोटेशन के तहत ये पॉजिटिव जी के अलावा जो है ग्रो करेगा और नेगेटिव जी पे डिके करेगा. Okay, so we have run into an issue which is very common in electromagnetics, and that is the issue of conventions. So there are two ways of writing phasors. One is by taking the time dependence to be iota omega t, and the other is representing it like, the one is with minus iota omega t, and the other is with plus omega t. So what's the effect of this thing? So if I choose this one, let's say the first one, and suppose I'm interested in plane wave, let's see what does this thing represent. So what does this thing represent? Let's say this is a real number. So when we take its real part, this becomes cosine omega t plus kc. And what does this notation represent when we have a phasor like this? This will represent cosine omega t minus. So this is a wave propagating along positive z-axis. This is a wave propagating along negative z-axis. Everybody understands that why this is propagating along positive and this is negative z-axis? Yes? Sorry? हाँ, अगर आप इसका प्लॉट देखें, let's say at t is equal to 0, they both have the same plot. At t is equal to 1, let's say this thing. This becomes cosine omega minus kz. So whatever was happening at z is equal to 0 will now happen at cosine omega minus, when t is equal to 1, this function becomes this. So the plot of this function is that whatever was happening at z is equal to 0 in this thing will now happen at omega minus kz is equal to 0, or z is equal to omega over k. So this is the plot at t is equal to 1 for this function. So when t is increasing, this function is moving in this direction. So this is a positive z moving wave, and this is a negative z moving wave. So the point is that the same phasor under one notation represents a wave moving along negative z direction, and the same phasor in the second notation represents a plane wave moving along the positive z axis. And the notation that we have chosen was that we chose exponential positive iota omega t. And under this notation, a wave minus iota kz represents a wave moving along positive z axis. So in this case, if we have a wave like this, this represents a wave moving along the k vector. Okay, because if we have this notation, then if it is a minus sign, it moves along minus. If it is a plus sign, it moves along plus. But here, if it is negative sign, it moves along plus k. If it is positive sign, it moves along negative k. So here it is moving along negative k, and if k is like this becomes like this, and this becomes like this. So let's see its plot. So the magnitude, जी कौन सी थी? ये वाली चीज, ये t0 पे तो ये फंक्शन है, ठीक है, तो ये प्लॉट आ गई। t1 पे ये t इक्वल टू 1 हो गया, ठीक है, तो यहाँ पे 1 रखा, ये फंक्शन बन गया। अब इसका प्लॉट हमने करना, एक तरीका तो ये है कि आप मैट्रिक वाला मेथड यूज करें कि z की वैल्यूज लेट्स से -10 से +10 तक -10 -9 पुट करते जाएं, ये वैल्यूड करें तो हर पॉइंट जो है वो लगा, ठीक है। दूसरा प्लॉट ये भी देख सकते हैं क्विकली कि जब z इक्वल टू 0 था इस फंक्शन में, तो ये 1 होता ना z0 पे, तो ये कब 1 होगा? जब ये 0 होगा, और ये 0 कब होगा? जब इसको 0 के इक्वल पुट किया। सो एट z इज इक्वल टू ओमेगा ओवर k, दिस इज 1, ठीक है, बल्कि यहाँ से आप इसकी वेलोसिटी भी बता सकते हैं। क्यों यासीन, कितनी वेलोसिटी होगी? डी ओमेगा डी के तो अभी हमने शायद निकाला नहीं है, शायद निकाला नहीं है, लेकिन यहाँ से आप बता सकते हैं इसकी वेलोसिटी ये ग्राफ से। जी वेलोसिटी क्या होती है? पहले तो ये देखो, वेलोसिटी होती है कि एक सेकंड में कोई चीज कितना मूव करती है, ठीक है। हाँ, क्योंकि ये देखें t इज इक्वल टू 1 सेकंड में ये पॉइंट यहाँ से यहाँ तक चला गया, और ये कितना डिस्टेंस है? ओमेगा ओवर k। So this is also the speed of the wave, which is omega over k. More precisely, this is not the speed of the wave, but for plane wave it's the speed of the wave, but actually it's the phase speed. Okay. So यहाँ पे आ जाते हैं. So under this thing, if this k double prime is positive, we have a situation like this, that the magnitude of E is like this, and the wave is propagating this way, and if the magnitude of k prime is negative, we have situation is like this. So the magnitude is decreasing towards z if k prime is negative, and it is increasing towards z if k prime is positive. In passive mediums, in the direction of propagation, the amplitude can only decrease because the energy is absorbed. In active medium, like blazing mediums, the amplitude can increase and decrease. Both things can happen depending on the sign of this imaginary part. Active medium, like blazing mediums, like a laser, because the medium can add energy into the wave. ये बोलो, ये देखिए, ये है ना फंक्शन, इसकी मैग्नीट्यूड जो है वो ये होगी, ठीक है। तो विद z इट्स एन एक्सपोनेंशियल फंक्शन। सो अगर k प्राइम पॉजिटिव है तो ये वाला होगा, अगर k प्राइम नेगेटिव है तो ये वाला होगा, ठीक है। सो द डिके एंड ग्रोथ डिपेंड्स ऑन k, एंड इफ k डबल प्राइम इज 0, देन व्हाट? देन इट्स कांस्टेंट. So the magnitude is constant for this plane wave. So let's take a couple of examples. Let's say we talk about dielectric material. And dielectric materials are material where mu is equal to mu naught, and epsilon is different than the epsilon of free space. So what is k? K, since k square came out to be omega mu epsilon, k is omega mu epsilon, and mu is mu naught, epsilon is epsilon relative into epsilon naught, so I put them here. You get mu naught, this thing, into epsilon naught. Let's call this thing as the wave number at in free space at the same frequency. And this thing is generally referred to as the refractive index. So for dielectric medium, the refractive index is equal to the square root of the relative permittivity of the medium. And the wave number is the product of the refractive index and the wave number in free space at the same frequency. And this is if this epsilon r is real. If epsilon r is complex, then epsilon square root is equal to n minus iota k, and this is called refractive index, and this is called extinction coefficient, because then k is k naught n minus iota k naught extinction coefficient. This is kappa. So this is the imaginary part of k and this is the real part of k. So if I put this k into the plane wave, the E becomes E naught exponential, there's a minus, minus, plus, iota square is minus, so minus k naught kappa z exponential minus iota k naught n z. So the wave is propagating along z axis and it's decaying as it is propagating along z axis if epsilon is complex. And just to give you an idea of different material, like if we talk about glass, glass has a refractive index in the range of 1.5 to 2. It can go above that because there are different types of glasses. So they have different refractive indices. Their extinction coefficient is almost zero because they are very good dielectric materials. Water, we all know, is 1.33, the refractive index. The extinction coefficient is almost zero. The permittivity is the square of this. And this is in the visible range, that the wave, the frequency of light is such that it is in the visible range. Now if I take another example, let's say silicon, at a wavelength of, free space wavelength of 250 nanometer, the epsilon r is minus 10 plus iota 11. And if I take its square root, this gives us 1.58 plus iota 3.6. So actually, this is also a trouble. Depending on the convention that we choose, that if we are working with exponential iota omega t or exponential minus iota omega t, the method of quoting the values of square root of permittivity is also different. If you are working with the exponential iota omega t that we have done today, then the permittivity is quoted such that its square root has a negative sign here, okay, because the negative here will then denote the decay along the direction of propagation. If you are working with exponential minus iota omega t, then you put a plus sign here. So this plus that I have put, and this is for exponential minus iota omega t time dependence. Anyway, so this imaginary part is 3.6 and the real part is 1.58. The same material, silicon, at another wavelength of lambda naught about 400 nanometer has an, let me write it here because I'm going down and down. At 400, the epsilon r is 30 plus iota 4, and epsilon r square root is 5.57 plus 0.387. So you see, in the same material, at a wavelength of about 250 nanometer, the propagation is very lossy because the extinction coefficient is 3.6. And the difference in phase speed in the medium and free space is very little because the refractive index is 1.58. The same material at another wavelength, the propagation is almost lossless because this number 0.38 is much less than this real number. And the phase velocity is much different in silicon than in free space because the refractive index is much higher than 1. Yes? How does it? जो property of material है जैसे refractive index, it depends on wavelength. At each wavelength, the refractive index is different in general. Follow कर रहे हैं? There is no mathematical relationship. They're all determined experiment. You can understand why they should depend. For example, let's say you think of a material. The material is made of electrons which are bound to the atom, going around the nucleus, quote unquote, and then possibly in general there are some electrons that are mobile, that can move around in the medium. So when you apply an electromagnetic field, if the wavelength of electromagnetic wave is, the frequency is very high, the electric field is changing very rapidly. The electrons that can go from here to, let's say, here, they can correspond very easily to the electric field. Actually, if the frequency is extremely high, the electric field is going on very rapidly, then nothing can respond to the electric field. Okay? So what happens that any material you take, the electromagnetic wave passes right through it. It's almost as if it is going through vacuum. Yes? If actually अब दूसरी तरफ भी हो रहा है ना, it's also is a particle. Okay, so if it happens to strike another particle, there would be a collision and ionization, other things can happen. But let's keep everything classical, that everything is wave, there is no particle picture. So the wave would pass right through it. That's why high energy electromagnetic waves like gamma rays, X-rays, they pass through everything. Even the gamma rays can even go right through the earth because it's almost like vacuum. And classically you can think of it as that the electric field is oscillating so rapidly that nothing can respond to it that quickly. But if the frequency is decreased a little bit, that now the electrons, let's say the bound electron, they can respond. So there is some dispersion. So the material is now seen by light in a different way. And if you bring down the field of oscillation even more, the other electrons, let's say the free electrons, can also come in. And then since there are several degrees of attachment of electrons to the atom, some electrons are attached more closely, like in inner shells. Some electrons are bound more loosely in outer shells. So that's why when we change the speed of oscillation of electric field, the number of electrons responding to it change. Usually at low electric field, for example DC electric field, the refractive index is the highest. Even though we don't call it refractive index, we call it then the permittivity of the medium, or usually dielectric constant, epsilon. If you apply electric field across a material, a constant electric field, every charge will respond. Because it's so slow that every charge has enough time to respond to it. So that's why usually the permittivity has a plot like this. Let's say the real part, it's something like this. So this is almost 1. So at lower frequency, the refractive index is highest. As the frequency increases, the refractive index goes on decreasing because the number of charges that can respond to the electric field decrease and decrease. But there's no mathematical relationship for this. For some material, it could be a little bit different, but that's the average behavior. Okay, so the important point that I wanted to convey from this thing is that don't think of a refractive index as property of a material, independent of everything else, but it depends on wavelength. And by wavelength I mean frequency, because frequency and wavelength are also related. Like K naught is 2 pi over lambda naught, and which we can also relate to, let's say, omega, which is 2 pi f, where f is C over lambda naught. So all these things are related. If we fix lambda naught, we are actually fixing the wave number. Okay. Let's take another example. Suppose we talk about aluminum. Aluminum for red light at 633 nanometer has a permittivity I'm sorry, in the notes I have provided these numbers for this time dependence, and the mathematics that we did was for the other time dependence. That's why you see a plus sign here, 1.3 plus iota 7. You see, in this case, the extinction coefficient is much higher than n. So this wave would decay away very rapidly. Let's say, try to find out how long the light can penetrate into aluminum. So this is K, this is N. So let's say this is the Z-axis. We shine red light on aluminum, and at Z is equal to 0 is the aluminum interface. So the electric field is E naught exponential minus kappa double prime. So this is K double prime, which is kappa into K naught Z exponential minus iota N K naught Z. Okay, so I replace K with N K naught minus iota kappa K naught. So the magnitude of the field is this. Suppose here is some magnitude, anything E naught. So let's try to compute the length, after which the magnitude comes from, let's say, maximum 1 to exponential minus 1, which is almost 0.33 of this value. So it has decayed to about 66% of its magnitude. So to do that, this number should be 1, kappa K naught Z should be 1 at this point. So if this is 1, then the light would have decayed to exponential minus 1 of its magnitude at Z is equal to 0. So Z is 1 over kappa K naught, and K naught is 2 pi over lambda naught. So lambda naught goes up. So we have lambda naught over 2 pi into kappa. So let's work out a number for aluminum. So this kappa is 7. So let's put 7 here. This 2 pi can be approximated as 6. So 7 into 6 is roughly 42. So in about 1 over 40 times the wavelength, the light would have decayed to 66% of its value at this point. And at 633 nanometer, this comes out to be so for simplicity, let's do it 600 and let's make it 40. So this is 15 nanometer. So roughly in 15 nanometer, the light would have decayed to 33% of its value at the interface. And let's say in another few nanometer, about 5 other nanometers, it would almost have gone to 0. So the light, that's why we say that light doesn't penetrate into the metals. It gets reflected from the interface, almost all of it. So only that energy will be lost from the incident wave, which is dissipated in this distance. Everything else will be reflected back. If we take an example of gold, at the same wavelength, gold has permittivity of minus 8.9 plus 1.2 I, and its square root is 0.2 plus iota 3. So first of all, you see the phase speed of plane wave in the gold is higher than the phase speed in vacuum. And that's okay, because the energy isn't going anywhere, it's only being consumed here. And its imaginary part is almost half that of aluminum. So the light may be able to go twice into gold as much as into aluminum. And also another thing you note that the real part of permittivity for metals is negative, right? Like here, like here. Silicon is metallic at smaller wavelengths, so that's why the real part is negative, and it's a lossy dielectric at higher wavelengths, so that's why its real part is positive. But for electromagnetics, it doesn't really matter whatever it is, because the tools and everything remains the same. If we have a magnetic medium, even though it's obvious, but I think it's worth doing it because sometimes people forget. If you have a magnetic medium, K is omega mu epsilon. For magnetic, this epsilon is epsilon naught and mu is mu naught into mu r. So this is, let's say, K naught. So now the refractive index and extinction coefficient are coming from the square root of the relative permeability. So I'm just writing it here because sometimes people engrave this thing in their mind that refractive index is the square root of permittivity. That's only true if it is a pure dielectric material. If it is a dielectric magnetic, then as you can see, K would be K naught, mu r, epsilon r, mu r. So this is the refractive index plus extinction coefficient, which is now the square root of the permittivity and permeability. So by the next lecture, I will actually think about a little bit about the convention, that if we should go with this thing or if we should go with this thing, and then we'll stick with that. Usually people who want to go with exponential iota omega t dependence, they write J instead of iota. J is also that same thing. But if you see a book and you see J, immediately it's exponential J omega t. If you see a book with iota, there's a possibility, higher probability that the book is using this convention, but still some people with exponential plus iota omega t also use iota. So with iota, people are using both things, but when you see J, that's for sure that they're using this convention. Usually, engineers prefer this convention, and physicists prefer this convention. So I'll make a decision and we'll change the notes as well accordingly, so that we stick with one notation and everything else remains consistent. Yeah. क्यों? खैर अगर J भी रखेंगे तो मैं तो I की लिखूंगा, मुझे भी I की आदत है. तो most likely we'll go with minus iota omega t. I'll actually have to redo the notes that I have made. नहीं, प्लस iota omega t करने से फिर ये है कि ये इसको मैंने इस तरह साइन चेंज करने के लिए माइनस आए. Generally, physicists would like to write it like this. Sheet में usually people make like Excel sheet. There's an NK column. They don't give any sign. It's up to you which convention you have used. You write it like that. So you take these quizzes, please. हमारे अभी 4-5 quizzes और हैं. So please don't come late or miss the class. Okay, वो किसी वक्त भी हो सकता है. जब मेरा दिल करेगा.